Hello, welcome to our ultrasound physics for MSK test preparation, and today we're going to go over the ultrasound concepts, variables, and parameters. And let's start with the ultrasound concept. Alright, the ultrasound is a sound wave which is not in the audible range. Of course we cannot hear it. It is impossible to hear ultrasound for the human ears. So we need to know that ultrasound goes over the audible range, and then this audible range goes between 20 hertz to 20 kilohertz. All right, that's what we call the audible range. So the ultrasound frequencies, the ones that we use today for our diagnosis field, is basically over 20 kilohertz. It's basically over 20 kilohertz. But let me tell you something, not all the frequencies above 20 kilohertz are going to be useful for getting ultrasound pictures. Okay, we have what we call the imaging range. Nowadays, for example, the imaging range is something between 2 megahertz and 21 megahertz. And let me tell you something, this number keeps increasing every year. And you know something, like when the frequency is so high, the resolution of the system is going to improve a lot, but then the penetration is going to be compromised. That's the problem with ultrasound nowadays. Like, all these high frequencies are pretty useful when you're trying to visualize pretty superficial structures, but if you're going to go deeper, then low frequencies are going to help you more. So don't forget about this principle, which is really important. If you have more frequency, then of course, yeah, resolution of your picture, of your images, is going to increase. But then this is the problem here. You're going to have less penetration. So that's in case of the linear or sequential array system. That's the one that used for MSK. So this system, because it uses a high frequency, then it's pretty useful when it comes to, you know, nerves, visualization, and tendons and ligaments, and, you know, joint spaces. But if you're going to go deeper, of course, you know, the convex is going to help you more. That's a low frequency transducer. So don't forget about this. You know, more frequency is going to give you better resolution, but then you're going to have less penetration. The other way around, you know, if you have less frequency, then you're going to have less resolution, but then you're going to have more penetration then. And well, that's the imaging range. So we have the audible range. We have all this information here. What else? What else we need to know about this ultrasound? All right, so the ultrasound is made of, you know, it's made of particles, and those particles, they organize in zones where the particles are together, and then zones where the particles are apart, like this. And then we have one more time another zone where the particles are together, okay? And then one more time another zone where the particles are apart. As you can see, they alternate this way. So it doesn't happen the way, like, you know, if you have one compression and then another compression and then a rarefaction. No, it's not going to happen that way. So you have all the time a compression zone where the particles are together, and then you have a rarefaction zone where the particles are apart. So these zones in here, we call them compressions. And this one here, we're going to call it rarefactions. Now this is pretty easy to understand. In compression, those particles are so tight together that in compression we're going to have high density and high pressure. It makes sense. So we're going to have high density, we're going to have high pressure. In the rarefactions, it's just the other way around. We're going to have low density and then we're going to have low pressure. So until now we can say the following: the ultrasound is a sound wave which frequencies are above 20 kilohertz, above the audible range. But the imaging range is going to go from 2 megahertz to 21 megahertz nowadays, and this number keeps increasing all the time. All right, there is this trade-off that says when you have more frequency, then resolution is going to go up, but then penetration is going to be compromised. Now the sound is made of compressions and rarefactions, where the compressions are high density, high pressure zones, and rarefactions are low density, low pressure zones. All right, so we're going to the next point right now, which is basically the ultrasound is a longitudinal wave. All right, the ultrasound is a longitudinal wave. And it is a longitudinal wave because these particles, they move in the same direction of the main axis of the wave. So they don't go like up and down, they don't go this way. No, they move in the same direction of the axis of the main wave. They move that way. So the ultrasound is a longitudinal wave. That's good to know. So the word that is going to help you here to understand is the word parallel. Parallel what? You know, the particles are parallel to the main axis of the sound wave. And then we need to know that the sound is a mechanical wave. It's a mechanical wave. It is. You know, mechanical wave, they need a medium to go through. And the ultrasound cannot go through the vacuum. So the ultrasound needs, like, for example, in its air, in its any type of tissue, in its blood, in its muscle, it needs a medium to go through, but it cannot go through the vacuum like the electromagnetic wave are able to do. So the ultrasound needs a medium to go through. That's good to know. So until now we have the ultrasound uses frequencies above 20 kilohertz, okay, or above the audible range. The image range goes from 2 megahertz to 21 megahertz. Mega, that's a million. So 2 million hertz, that's a lot. From 21 million hertz, that's the frequency range for the imaging range. And we say that the if the frequency increases, then the resolution is going to increase, but then the penetration is going to be compromised. The sound is made of rarefactions and compressions, where the rarefactions are low density, low pressure zones, but the compressions are high density, high pressure zone. That's good to know. The ultrasound is a longitudinal wave because the particles, they move parallel to the main wave. And it is a mechanical wave because it needs a medium to go through. So that's good to know. So we have the whole concept in here. And in addition to this, we may say that the ultrasound is a pressure wave that moves energy from point A to point B. All right, to point A to point B. Perfect. So that's the ultrasound concept. Then we're going to move to the next topic, which is basically the acoustic variables, right? So we're going to have and then we have three of them. We have one, we have the pressure, all right? Then we have number two, we have the density. And number three, we have the particle motion or distance. So as you can see it, if we go back to this explanation of the compressions and rarefactions in here, so compressions, and then we have rarefactions one more time, you know, those variables are constantly changing. They have this rhythm, all right? They have this rhythm where, you know, sometimes pressure is high and then pressure is low, then pressure is high, then pressure is low. Makes sense. They have this rhythm. That's why they're acoustic. So density the same way, you know, density here is high, but density here is low, but density here is high, but density here is low, all right? And the same for the particle motion or distance. You know, sometimes the particles are close together with the distance is being reduced, and then the particles are apart where the distance is, you know, is greater now. So pressure, density, and particle motion, those are the acoustic variables, all right? So just let's talk a little bit about the concept for pressure. That's when you apply one force over an area, okay? Force over the area. So density is, you have grams per cubic centimeters. So you're basically putting some mass in a volume. And of course, particle motion or distance, we're going to use centimeters or millimeters or any unit of distance. So it makes sense. So those are the acoustic variables, all right? So next we're going to move to the acoustic parameters. And to study the acoustic parameters, we need to separate this into acoustic parameters that they have to do with a continuous wave and the acoustic parameters that they have to do with the pulse wave. Let's begin with the acoustic parameters that they have to do with a continuous wave. So let's get this continuous wave, all right? And in order to understand this, we need to know first what a cycle is. And what is a cycle? It's just basically this here. It's something that repeats once and once again. Like, for example, this wave has 1, 2, 3, 4, 5, 6, and 7 cycles in total. Now those cycles are going to have their own parameters, right? This wave is going to have its own parameters. Let's say, for example, the first one that we're going to take a look is the period. And then the period is just basically time. Time for what? Time for the cycle, right? Time for the cycle. So we're talking about the time here. All right, so then the next parameter is going to be the frequency. Which is basically how many cycles of those you have in 1 second. So frequency is how many cycles you have in 1 second. Like, for example, if I give you wave A and then I give you wave B right here. This is wave A. And this is wave B. So it makes sense that wave A has more frequencies, has more cycles per second. And then wave B has less frequency, has less cycles per second. But the time for the cycle here is longer compared to the time for the cycle here. There's one important relationship between period and frequency. It says the following: if period goes up, then frequency is going to go down. All right, so they are inversely related. It's just the other way around. If period goes down, then the frequency is going to go up. That's why period equals 1 over frequency and frequency equals 1 over period. The units that we use for the period are microseconds. And for frequency, we're going to use megahertz. So we're talking about many, many cycles in 1 second. And those cycles are going to last for, pretty short period of time that we prefer to use microseconds, which is 10 to the negative 6th. Or microseconds is 1 times 10 to the minus 6 in here. It's pretty small, pretty small time in here. It's pretty small time. So we have period, so we have frequency, and then we're going to talk about 3 parameters that they are adjusted with the same setting in your system. Those 3 parameters are amplitude, we have the intensity, and of course then we have the acoustic power. So all these 3 parameters in here, they're adjustable, all right? And they tell you how powerful your wave, your acoustic wave is. They're adjustable using your output power setting. All right, and of course, if this output power goes up, the amplitude is going to increase, and the wave, the intensity is going to increase, and then the power is going to increase as well. So what is amplitude? So the amplitude is how high your wave is. Like if, for example, I give you wave A and I give you wave B. So this is A here. And this is wave B. In a way, it has more amplitude because there's more height in the wave. And it doesn't matter how many cycles in 1 second it has, the frequency and the amplitude, they don't have any type of relationship. You may have a waveform that has a high frequency with low amplitude, or maybe you have a low frequency wave that has, high or low amplitude. Doesn't matter, so they're not related. So that's what we call the amplitude, how high your wave, how strong your wave is. Now moving next, intensity. What is intensity? All right, so intensity is when you concentrate a power over one area. And that's why the intensity units are watts per centimeter squared. All right, so intensity is something that we measure along the sound beam. And this is the sound beam in here. It looks in the space this way. It has one part that we call the focal point right here. And this is the highest intensity area. Makes sense because right here at the focal point, the area is small. Now look at this. If area goes down, intensity goes up. So basically all the power of a wave has been concentrated at the focal point. That's good to know. And in our system we use 1 focal point, 2 focal points, sometimes 3 focal points. We have to be careful with the frame rate because if you use many focal points, the frame rate is going to be degraded. Alright, so that's basically the intensity. And then of course the power, which is our next parameter. Power is just basically the work performed by the wave. But this sounds like to a scientist, right? It's better to say that the power is just how strong your wave is as well. So those 3 parameters, they say the same thing about the wave. They say, hey, this wave is pretty strong. This wave is has a lot of intensity, has a lot of amplitude, has a lot of power. Okay. So until now we have frequency, then we have period, then we have amplitude, then we have intensity, and then we have power. We have 5 parameters in total, but we still need 2 more. And those are, we have we have the propagation speed. All right, so we have the propagation speed. And that's number 6, and then we're going to have number 7, that's the wave length. You know, where's the propagation speed? It tells you how fast the sound moves through the matter, and in this case through the tissues. And this propagation speed does not depend on anything that you do in your system. All right, the propagation speed depends on the medium. It depends on the stiffness of the medium. So the sound is going to move faster through solids, and it's going to move pretty slow through gases. And it depends on the density of the tissues, all right? And the propagation speed will be directly related to stiffness, as I said before, and it will be inversely related to the density. So the highest propagation speed of the sound happens when you have high stiffness with low density. And that's the propagation speed as a property of a medium, all right? And we're going to move to the wavelength, all right? Wavelength, which is represented by this letter that we call lambda, and it will be the propagation speed, which is represented with this C here, divided by the frequency of the sound, all right? And it makes sense. Look at this. If frequency goes up, then wavelength is going to go down. They're inversely related. Let me show you this example in here. You will understand this a lot better. We're going to have a high frequency wave in here, and we're going to have a low frequency right here. Now, what is the wavelength? The wavelength is the distance from a peak of a cycle to the peak of the next cycle from here. And then this is the wavelength in here. And if you can see it in here, A has more frequency, but then the wavelength is short. They're inversely related. And then for B, then you have less frequency, but then you have a longer wavelength. It makes sense. So they're inversely related. So this relationship is really important, because later we're going to learn about the axial resolution, and the axial resolution is better when the frequency is high, which is going to result in a shorter spatial pulse length that we're going to study later. So we have this acoustic parameters. We have 7 of them, all right? So we have period, we have frequency, we have amplitude, we have intensity, power, we have propagation speed, and then we have wavelength. Perfect. And then we have the 3 acoustic variables, all right? They are pressure, they are, we have also the density, and then we have the particle motion. Perfect. So we have, and also we have the ultrasound concept until now. All right, perfect. So we have all this information in here. I think our next tab is talking about the parameters, but for the pulse wave. Let's move to the pulse wave now. All right, so this wave in here, the continuous, the machine cannot make a picture with this. The machine needs what we call the on and off time. It needs a pulse wave. All right, it needs the ringing time or transmission time in here, which is the on time, and it needs the listening time, which is basically the off time. And it doesn't mean that your system is off. Your system is working. It's just like it's listening, is waiting for the echo, and then is making all of this processing to give you the picture. Remember, this happens pretty fast. It happens real fast. Now, the acoustic parameters that have to do with this two, I may say these two spaces of time are, for the on time we have the pulse duration. The name tells you how long the pulse is, the on time is. And we have the spatial pulse length, which basically tells you how long is the pulse in the space. How long is the pulse in the space? You know, the pulse duration, if we're gonna get it, it's gonna be easy to get it. We're gonna get the number of cycles in the pulse times the period. That will give you how long is this pulse in time. The SPL, you're gonna get the number of cycles times the wavelength. It makes sense. Length is distance. If we multiply how many cycles we have in this pulse times the length of the cycles, and of course you're going to have your spatial pulse length. So those are the two acoustic parameters of the pulse wave that they have to do only with the on time. And let's move to the parameters that are going to include the off time. Alright, so we're going to have the pulse repetition period, pulse repetition frequency, and then we're going to have the duty factor. You know, the pulse repetition period is just basically the on time plus the off time. It will be the time from the beginning of this pulse to the beginning of the next pulse, which is this entire time in here. Let me tell you something. The on time, this one cannot be changed. But this one here, we are able to change it. How do we do it? There's one setting in your system that we call depth. And it makes sense if you're going deeper. If you're going deeper, your listening time is going to increase. And then, of course, deeper view will give you more pulse repetition period. It makes sense. So because your off time is going to be longer, this one is going to be longer here. But then the pulse repetition frequency is how many pulses you have in 1 second. Like for example, if I give you wave A, then I give you wave B. Alright, so it makes sense. A is going to have more pulse repetition frequency, and B is going to have less pulse repetition frequency. But then, of course, you know, if A has more pulse repetition frequency, it's because it's working like this. Boom, 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 boom. It's pulsing so fast. Boom, 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 boom. The off time is pretty short. So that means if you have more pulse repetition frequency, then you have less pulse repetition period. And then the other way around would be, so B is working like this. Boom, boom, boom. It's just going deeper. It's going deeper. So A, for example, is going to maybe your common extensor or your common flexor in the elbow, pretty short distance, but maybe B is going to the hip, and then that's why, you know, the off time is longer, because the sound is going farther away. All right, so then you have here less PRF, which is basically more PRP, meaning something, right? The pulse repetition period and the pulse repetition frequency are inversely related. They are inversely related. All right. Okay, so A means is working superficial, and then B is working deeper. Yes, that's good to know. So for now, we can tell the following. If we are going superficial, boom, 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 boom. Then we have more pulse repetition frequency, but then we have less pulse repetition period. And then if you're going deeper, your wave is going like this, boom. And it has to wait for, your system has to wait for the echo. Then it goes like boom. More pulse repetition period, but then less pulse repetition frequency. Makes sense. So now what is duty factor? Right here, duty factor basically relates the time that the machine is working compared to the time when the machine is like basically listening. So the duty factor is going to be a ratio between the on time versus the entire time. So that's why we say the following. So duty factor equals the pulse duration over pulse repetition period times 100. And the duty factor in our system is pretty short. It's usually like 0.001 or 0.1%. That means that most of the time your machine is listening. Alright, most of the time your machine is listening, and it's kind of a lazy system. The on time is pretty short. It's not lazy at all. It works a lot. But it's just a nice way to remember when you're studying all of this here. So at the end of the day, I want you to remember the following. That's important to know. If depth increases, then your system is working like this. Boom, boom, boom. All right, so that means, so the off time is longer, making the PRP longer. And if the PRP goes up, of course, the pulse repetition frequency goes down. And this combination here has a low duty factor. Your machine is just waiting a lot, right? So you're going deeper. And the other way around, if you're going superficial, then your system is working like that. Pum, 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 pum. It's just going, pretty short time, pretty short off time. All right, then, the PRP is going to decrease pulse repetition period. Then the pulse repetition frequency is going to go up. And then, of course, this system is working more. It has a value for the duty factor, which is going to be greater. So that's good to know. This is a really important information. So, today we talked about the ultrasound concept. That's good to know. The ultrasound is a pressure wave. It's made of compressions and rarefactions. The compressions are the high density, high pressure areas. The rarefactions are low density, low pressure areas. So we have the acoustic variables. So we have pressure, we have density, then we have particle motion or distance. We have acoustic parameters for the continuous wave. All right, so we have period, frequency, amplitude, intensity, and power. We have propagation speed, and we have the wavelength. And then we have this acoustic parameters for the pulse wave. We have the pulse duration, the spatial pulse length for the on time. And then for the combination of the on and off time, we have the pulse repetition period, pulse repetition frequency, and duty factor. And then this relationship between depth and this parameters is really important to know. This is something that we apply every day when we work, when we change the depth. Your system is doing all of this. So thank you for being with me in this first lecture. We still need to talk about more. Next time we're going to talk about resolutions and axial. We're going to talk about lateral. Then we need to talk about temporal frame rate. We're going to go over the also we're going to go over the adjustments in your system, how to fix the dynamic range, how to fix the overall gain. And then later we're going to talk a little bit about Doppler and then artifacts as well. So keep in touch with me, and then we're going to have fun. All right. Thank you so much.